Hello, chemistry students. All right, today we're going to continue our discussion on photoelectron spectroscopy, also known as PES. All right, and just as a reminder from our class discussion, these peak heights right here represent the relative number of electrons, or the number of electrons, and the binding energy down here represents how close these electrons are to the nucleus. So if it requires a lot of binding energy, that means it's very close to the nucleus. So we're going to label this over here, nucleus. And the electrons that are further away from the nucleus, or the farthest away from the nucleus, are the easiest to remove because they're further away. So we're going to call these the valence electrons. All right, and just as a reminder, our force, this is Coulomb's law, is proportional to Q1 times Q2 divided by R squared. We'll talk about this more on B. All right, so the further we are from the nucleus, the less energy that it will take to remove it, or the less force. All right, okay, so this is the nucleus over here. The energy level that is closest to the nucleus is energy level 1 and sublevel S. So since there are electrons further away from the nucleus, and this is a ground state atom, which means it's not energized, all the electrons are in their ground state, following off-bell principle, the 1s has to be filled before you start filling up the next energy level. So that means the 1s has to have 2 electrons. And it shows here there's 1, 2. Sometimes you won't see these grids on here, but just know that the 1s has to be filled before you start filling up any other ones. All right, so we filled up the 1s with 2 electrons. The next energy level is energy level 2, sublevel S. This 2s peak right here is the same height as your 1s, so we're going to put 2 electrons there. The next sublevel is P, and these 2 peaks are very close together, which is usually indicative that it's the same energy level, which is 2. 2p, this peak height right here is 3 times the peak height of your 2s. So we can say 3 times 2 is 6. You can also look at this as saying 1, 2, 3, 4, 5, 6. So it has 6 electrons. The next energy level is 3, sublevel S. And again, your S, 3s is the same height as your 2s and your 1s, so it's going to be 2. And the next energy level and sublevel is 3p. And we're going to go ahead and count this peak height. 1, 2, 3 electrons. All right, so our superscript here will be 3. There are a couple of things that I want you to notice here before we move on. Okay, so the difference between the 1s and the 2s in energy is, the binding energy right here, is much greater than the difference between your 2s and 2p. All right, so there's a lot of energy right here compared to right here. And again, between your second energy level and your third energy level, there's more energy difference between each energy level than there is between the sublevels on an energy level. All right, now that we have our electron configuration, we can easily figure out what element this is. So there are a couple of different ways we can do that. One way is to look at your valence shell electrons right here. And it's on the third energy level, and it ends in 3p3. So you can go to the third period and go over to groups 13 through 18, and then start at 13 and count over 3 electrons, or 3 spaces, because it has 3 electrons. You'll see that that is phosphorus, if you look on the periodic table. All right, the other way that you can do that is count up electrons. So this is a neutral atom, so the number of electrons has to equal the number of protons. So we have 2 electrons here, plus 2 electrons here, that's 4. And we have 6 electrons here, so 4 plus 6 is 10. Then we have 2 electrons here, 10 plus 2 is 12. And we have 3 electrons here, so 12 plus 3 is 15. So if we look on the periodic table, we'll see that the element that has 15 protons is phosphorus. Now let's go on to part B. All right, part B says to consider the element in the periodic table that is directly to the right of the element identified in part A, which we've already said was phosphorus. So the element that, if you look on the periodic table, the element that is directly to the right of phosphorus is sulfur, and it has an atomic number of 16. And this is asking, would the 1s peak of this element appear to the left of, to the right of, or in the same position as the 1s peak for phosphorus, and then explain your reasoning. So we've already determined that this peak right here is for phosphorus, and it is the 1s peak, and that's what the question is asking us to focus on, is the 1s. So basically we need to find out to the left of right here, the same as, or to the right of the phosphorus peak. And that's basically your x-axis. So we're looking for the binding energy, or the energy required to keep the electron to the nucleus, or attracted to the nucleus. So the best thing to do right here is to look at Coulomb's law. So that's what we're going to do. So for phosphorus, our force will be proportional to our charge 1, which is going to be an electron, so I'm going to say a -1, times our charge 2, which is going to be our nucleus. All right, and since it's in the 1s sublevel, this electron right here is going to exhibit the full force of the nuclear charge, because it is very close to the nucleus and there is no shielding. So the full charge of the nucleus for phosphorus is a +15. All right, and that's going to be divided by r squared. So we're going to say that that's proportional to a -15, all right, which is an attractive force because this is a negative number. Now let's look at the force, or the binding energy, for sulfur. So our force for sulfur is going to be proportional to the electron in the 1s, and it too is going to feel the full charge of the nucleus, which is 16 protons. The distance between the electron and the 1s and the nucleus is going to be about the same for each of these elements. It's not the same, but we're going to say that it's about the same. So this would be a -16, which is an attractive force, or your electron in the 1s for sulfur is feeling more of an attractive force towards the nucleus than your phosphorus is, which means if it's feeling more of an attractive force, it will be to the left of the 1s. So I'm going to draw it right there. All right, guys, we're done.